What if the laws of physics that govern everything around you, the same laws that explain why your coffee gets cold, why smoke drifts upward, why the universe itself is slowly winding down towards silence and stillness, what if those laws were only telling you half the story? What if buried inside the most extreme objects in the cosmos, objects so dense and so warped that not even light can escape them, there was a process happening that our best theories completely missed, a process that keeps going long after everything else has stopped, long after the stars have burned out, long after the galaxies have gone dark, long after the universe itself has reached what physicists call the heat death, that final frozen state where nothing meaningful ever happens again. What if black holes never truly stop evolving? What if they have a secret life that continues for an almost unimaginable length of time, driven not by heat, not by energy, not by anything we normally associate with activity and change, but by something far more subtle and far more profound, something that connects the physics of the cosmos to the mathematics of computers, to the logic of encryption, to the deepest questions about the nature of quantum reality itself. That is exactly what Stanford physicist Leonard Susskind discovered when he began staring at a diagram that made no sense, and what he found when he went looking for an answer changed the way physicists think about black holes, about complexity, and about the ultimate fate of the universe. To understand what Susskind discovered, we need to start with something that seems completely unrelated to black holes. We need to start with steam engines. In the 19th century, engineers and scientists trying to build better and more efficient machines stumbled onto one of the deepest principles in all of nature. They were trying to understand why no engine, no matter how well designed, could ever convert heat into work with perfect efficiency. And the answer they found was entropy. Entropy is, in the simplest possible terms, a measure of disorder. A measure of how many different ways the microscopic components of a system can be arranged while still producing the same overall appearance at the large scale. A glass of ice water has low entropy. The ice is structured, organized, its molecules locked in precise crystalline patterns. As the ice melts and the water warms toward room temperature, entropy increases. The molecules spread out, their arrangements become more random, more disordered, and the system moves toward what physicists call thermal equilibrium, a state where temperature is uniform throughout and no more useful work can be extracted. This is the second law of thermodynamics, one of the most fundamental and most robust laws in all of science. Entropy always increases, systems always move toward greater disorder, and once a system reaches thermal equilibrium, it stops changing in any meaningful way. Applied to the entire universe, this law leads to a deeply unsettling conclusion. The universe itself is a closed system. It contains a finite amount of energy, and over an almost incomprehensibly long time, that energy will spread out uniformly. Stars will exhaust their fuel. Black holes will eventually evaporate, and the cosmos will settle into a state of perfect thermal equilibrium, a state physicists call the heat death of the universe, a state of maximum entropy, maximum disorder, and zero meaningful change, a dead universe in every sense that matters. But here is where Susskind's puzzle begins. When he looked at the mathematical diagrams used to visualize the geometry of space-time around the black hole, something did not fit. These diagrams, called Penrose diagrams, are a kind of map of the entire universe, including the black hole and its interior. And what Susskind noticed was that the interior of the black hole, the region of warped space-time inside the event horizon, was not static. It was not sitting at some fixed size, waiting for the black hole to eventually evaporate. It was growing. The interior of the black hole seemed to start at some smallest size and then expand, bouncing and stretching outward in a way that continued for an extraordinarily long time. Susskind kept asking colleagues what was growing inside the black hole, and nobody had a satisfying answer. They would say it was just the volume of the black hole interior. But that answer explained nothing, because the second law of thermodynamics said the black hole should reach thermal equilibrium relatively quickly, its entropy should max out. And once entropy maxes out by the standard logic of physics, nothing should keep changing, and yet the interior kept growing. There was a profound mismatch between what the equations of general relativity were showing and what the laws of thermodynamics seemed to permit. Something was happening inside black holes that the existing framework of physics could not explain. To understand where Susskind found his answer, we need to understand something about quantum systems and why they are so fundamentally different from classical ones. In classical physics, describing the state of a system is straightforward. You list the positions and velocities of all the particles, or in the language of information theory, you list all the bits, each one either 0 or 1. The state is fully captured by these individual descriptions. But in quantum mechanics, this approach breaks down completely. Quantum systems are described not by individual bits, but by qubits, quantum bits, that can exist in superpositions of 0 and 1 simultaneously. And crucially, qubits can be entangled with each other in ways that have no classical analog. When qubits are entangled, the state of the system cannot be described by looking at each qubit individually. The information is stored globally, in the correlations between qubits, in a way that is distributed across the entire system at once. This means the space of possible quantum states is exponentially larger than the space of classical states. Richard Feynman understood this deeply. He recognized that if you have a system of qubits, the number of orthogonal quantum states available to that system is not just large, it is exponential in the number of qubits. The system begins in some simple state and then starts wandering through this vast space of quantum possibilities, exploring configurations of growing intricacy and complexity for a time that dwarfs the timescale on which thermal equilibrium is reached by an enormous factor.
This is the key insight that unlocked Susskind's puzzle. Thermal equilibrium is reached when the classical entropy of a system has maxed out. But reaching thermal equilibrium does not mean the system has stopped evolving. It means the coarse-grained, large-scale description of the system has stopped changing. At the microscopic quantum level, the system is still evolving. Quantum entanglement is still growing and shifting. The quantum state is still wandering through its vast space of possibilities, becoming more and more intricately structured, more and more deeply entangled, more and more complex in a precise mathematical sense. Even after the coffee and the milk have mixed and the thermodynamic arrow of time appears to have stopped, the quantum complexity of the system is still increasing. And it will keep increasing for an exponentially longer time before it too reaches its maximum.
Susskind realized that this quantum complexity, this measure of how intricate and deeply entangled the quantum state of a system has become, was exactly what was growing inside the black hole. The size of the black hole interior was not tracking entropy, it was tracking quantum complexity. And that realization changed everything. To make this precise and to communicate it to the scientific community, Susskind and his collaborator Adam Brown turned to a concept from theoretical computer science called quantum circuit complexity. In computer science, circuit complexity is a way of measuring how complicated a computation is. Specifically, how many elementary logical operations you need to perform to produce a given output from a given input. In quantum computing, quantum circuit complexity measures how many elementary quantum gates you need to apply to transform one quantum state into another. A simple quantum state has low complexity because you can reach it from some reference state with just a few operations. A highly entangled, deeply structured quantum state has high complexity because reaching it requires an enormous number of operations. Susskind and Brown proposed that the quantum circuit complexity of the quantum state of a black hole is directly proportional to the volume of the black hole interior. As the quantum state of the black hole evolves and becomes more complex, the interior of the black hole grows, complexity and geometry are connected. The mathematics of quantum computation is describing the physics of space-time inside a black hole. This was a genuinely radical idea. It was drawing a bridge between two fields that had no obvious reason to be connected: theoretical computer science on one side and quantum gravity on the other. When Adam Boulin, a computer scientist at Stanford, first heard this proposal, he was skeptical. The connection between something as physical and geometric as the volume of a black hole interior and something as abstract and computational as quantum circuit complexity struck him as deeply implausible. Circuit complexity is notoriously difficult to compute. It is one of the hardest quantities to reason about in all of theoretical computer science. Why would nature choose to encode something so computationally intractable as a geometric property of space-time? But Boulin and his collaborators decided to take the conjecture seriously and tested rigorously using tools from modern cryptography. They noticed that the quantum states Susskind was considering behaved in ways that closely resembled a quantum analog of a block cipher. The the type of encryption algorithm that underpins most of modern digital security, including the technology behind cryptocurrencies. A block cipher works by scrambling information in a way that is extremely difficult to reverse without the correct key. The scrambling is chaotic and complex, and the complexity of the scrambled output is directly related to the number of operations the cipher has performed. Bowen's team found that by analyzing this analogy carefully and applying the mathematical tools developed for understanding cryptographic security, they could test whether Susskind's conjecture was internally consistent. And what they found surprised them. Rather than finding a contradiction or a flaw in the proposal, their analysis supported it. The mathematics of cryptography, of all things, was pointing toward the conclusion that quantum circuit complexity was indeed the right quantity to describe the evolution of a black hole interior. A proposal that had seemed implausible turned out to have deep mathematical support from an entirely unexpected direction. Armed with theoretical support for the connection between quantum complexity and black hole geometry, Susskind and his collaborators took the final step. They proposed a new fundamental law of physics. They called it the second law of quantum complexity, formulated in direct analogy with the second law of thermodynamics. Just as the second law of thermodynamics says that entropy increases until it reaches its maximum at thermal equilibrium, the second law of quantum complexity says that quantum complexity increases until it reaches its maximum at what you might call complexity equilibrium. But the time scale on which complexity reaches its maximum is exponentially longer than the time scale on which entropy reaches its maximum. This means that long after a black hole or any quantum system has reached thermal equilibrium, long after its classical entropy is maxed out and it appears to have entered a kind of heat death, its quantum complexity is still growing. And it is this growth of quantum complexity that drives the continued expansion of the black hole interior. The black hole is not dead after thermal equilibrium. It is still evolving, still becoming more complex, still growing on the inside, because its quantum state has an almost limitless amount of complexity left to develop before it too reaches its maximum. What makes this proposal so striking is not just what it says about black holes, but what it implies about the nature of reality more broadly. For decades, physicists have approached quantum systems by starting from classical descriptions and then adding quantum corrections, treating quantum mechanics as a modification of classical physics rather than as the fundamental starting point. What Susskind's work and the work of those who have tested and extended it suggests is that this approach misses something essential. When you fully embrace the quantum nature of the universe, when you stand inside the quantum world and use genuinely quantum language to describe quantum systems, you find structure and richness that the classical approximation cannot see. Quantum complexity is one of those hidden structures. It is something that simply does not exist in classical physics. It is a purely quantum phenomenon. And yet it may be driving the evolution of the largest and most extreme objects in the universe. The second law of quantum complexity, if it holds, also has implications for the ultimate fate of the universe. The second law of thermodynamics tells us the universe is heading toward heat death, toward a state of maximum entropy and zero meaningful change. But if quantum complexity continues to grow long after entropy has maxed out, then heat death is not the end of the story. There is a second chapter, a vastly longer chapter, during which quantum complexity drives continued evolution of quantum systems even in a universe that has otherwise gone cold and dark. Eventually, after an exponentially long time, quantum complexity too will reach its maximum. And at that point, what happens? Susskind himself has reflected on this with a kind of wondering openness. He has suggested that after an almost incomprehensibly long time, quantum fluctuations might drive complexity back down again, returning systems to simpler states. The story might begin again. The universe might in some sense reset. Everything that has ever happened might happen again, because if you wait long enough, every quantum state that the system can occupy will eventually be revisited. This is a deeply strange and deeply provocative idea, but it emerges naturally from taking the quantum world seriously, from following the mathematics of complexity wherever it leads. We are at an early stage in understanding what the second law of quantum complexity really means for black holes, for the universe, and for physics as a whole. Susskind himself is careful to say that it is a conjecture, not a proven theorem. The analogy with the second law of thermodynamics is compelling, and the mathematical support from complexity theory and cryptography is encouraging, but the full implications remain to be worked out. What is clear is that something profound is happening at the intersection of quantum mechanics, general relativity, information theory, and computer science. The tools of theoretical computer science developed to understand the limits of computation and the security of encryption algorithms are turning out to be essential for understanding the physics of black holes and the nature of spacetime. Quantum complexity, a concept invented to measure how hard a computation is, may be written into the geometry of the universe at the deepest level. And a new law of physics, the second law of quantum complexity, may be needed to describe a universe that is stranger, richer, and more enduring than even our best theories have suggested. The universe is not winding down as simply as we thought, black holes are not as dead as they appear, and the mathematics of quantum complexity is revealing a cosmos that keeps evolving, keeps growing, keeps becoming more intricate and more deeply structured, long after the lights have gone out and long after everything we can see has gone silent. The second law is not the end of the story, it is only the beginning of a much longer and much more remarkable one.